Hello, I'm Dr. James Dborin, co-founder at DoubleWord AI, and we're back with another Behind the Stack video where I'm going to be talking about the use of speculative decoding in batched inference. So at DoubleWord, we've recently released a batched API which offers low-cost, high-throughput LLM inference with a 24-hour SLA, and I'm going to be talking about how we use speculative decoding in the back end of this stack in order to make that inference faster and cheaper. So we're going to be covering three things. We're going to do a quick recap of speculative decoding, which we covered in a previous video. We're going to talk about what limits high batch throughput and how speculative decoding can overcome some of those limitations. And then we're going to be talking about a batch API specific form of speculative decoding that we work on here at DoubleWord. So let's start with a recap on speculative decoding. So speculative decoding works by having two models working in tandem. A draft model, which is some small, cheap source of tokens that you run auto-regressively to get a response, some sort of response to a prompt. And then you have your big model, like the model you actually care about. And the input to the big model during decoding phase is not a single token at a time. It's not run purely auto-regressively, but we pass in the response from the small model. And the job of the big model is simply to verify that it would have done the same thing. So in this case, we pass in these three tokens, A, B, C. The big model verifies that it would have produced A. It verified that it would have produced B, and then it says it wouldn't have produced C and would have produced D instead. So in this single forward pass of the model in parallel, we get three tokens, whereas in normal decoding, you would get one token. What dominates this inference time is the weights of the model being pulled in from VRAM, and that doesn't change when you're running with three tokens instead of one. And so in this case, our inference is sped up by 3 times. 3 times faster because it takes the same time to pull in the weights. We get 3 tokens instead of 1 token. So speculative decoding has historically been applied to really low latency inference, delivering inference with the lowest end-to-end latency as possible, because of this fact that especially during decoding, when we are bandwidth bound, and the only time that really dominates is pulling in the model weights, that if I can get multiple tokens out of this, I get an immediate speed up. My token speed is ultimately bound by the time it takes to pull in the weights from VRAM into the SMs of the GPU or similar. Typically, this hasn't been used for high batch inference, for high throughput inference at high batches, and the reason tends to be that, especially with older open source models, they tend to get very quickly limited in what regimes the inference is still bottlenecked by pulling in the weights from the streaming multiprocessors. So what I mean is that when we do LLM inference, pretty much all the time is dominated by either the feed-forward layers or the attention operation. And if we focus on the feed-forward layers, what happens is that at some point, there's some number of tokens that when you run in parallel, the flops needed for the feed-forward to happen is higher than the time it takes to complete the flops or complete the maths of the MLP is higher than the time it takes to pull in the weights for that MLP. This ratio is known as the arithmetic intensity of the operation, and it kind of tells you how many tokens you might need in order to switch from this regime where you're bound by moving the weights to bound by completing the maths. And in large, dense models, this arithmetic intensity tends to be a few hundred tokens. So at a few hundred tokens, you switch from becoming bandwidth bound to becoming compute bound. So if we run, let's say, at a batch size of 64, in this case, we're still bandwidth bound. However, if we do speculative decoding, and with each of these, we include 5 draft tokens, which would be quite low. We include 5 draft tokens with each batch. Suddenly, we're going to be at about 300 tokens, and now there's a high chance that I am going to be approaching becoming compute bound on this hardware, on this particular hardware. And once you're compute bound, speculative decoding no longer gives you any benefits. As you increase the number of tokens that you're putting into your batch to speculatively decode off of, you're linearly increasing the amount of time it takes for that operation to finish. So you're no longer getting this free lunch where I can run this small model ahead, get 20 tokens per request, put them in, and for the same price as inferencing just 1 token, I can get 20 tokens. Like, you leave this regime quite quickly, especially at high batches. And this isn't a particularly high batch size either. So if you were running at a very high batch size, 128, 256, up into like thousands of requests running in parallel, you can very quickly see that you're going to run out of headroom in these compute-bound decoding regimes. So this is for dense models, and dense models include like the Llama 3 series, the Gemma 3 series. However, there's an interesting shift away from these models in the open source now towards sparse MOE models. I'm not going to get into what we mean by MOEs, or like the details of this, but what's important to note is that when you use a mixture of experts model, your arithmetic intensity, I'll call that AMOE, so the arithmetic intensity of the MOE is equal to the arithmetic intensity of the dense model. That would be the arithmetic intensity of the dense model if it just had one of the experts in the MOE, times by the number of experts, divided by the number of experts per token. And so we already said that this tends to be sort of a few hundreds. And then for open source MOE models, this might be something like 128, and this might be something like 4. This could be even higher, it could be 256, and so on. The result of this is that because the number of experts tends to be so much higher than the number of experts per token, that the arithmetic intensity of MOE models, the point at which they are they switch from becoming bandwidth bound to compute bound, is at a much higher batch size, which means that speculative decoding can be useful for much longer into much higher batch sizes. And in fact, what starts bottlenecking MOE bandwidth at high, or MOE inference at very high batch size, tends to be your KV cache. So we've talked about KV caches a lot in these videos. If my KV cache can fit, let's say, 1 million tokens, and I have a request that takes 1,000 tokens input and output, so it's 500 in, 500 out, let's say, or 800 in, 200 out, something like that. Then I can fit 1,000 requests in my KV cache and can run 1,000 requests simultaneously. If instead each request takes 100,000 tokens, which wouldn't be too out of the ordinary for a very long reasoning task, or maybe RAG over very long documents, then suddenly I can only fit 10 requests in my KV cache. But for example, for Quen 30 billion, A3B in FP8 on a H100, this arithmetic intensity threshold is around 5,000 tokens. So you can see that even for very short requests, you sort of get nowhere near this limit. But what's bottlenecking you in this case is the fact that that you just can't fit enough requests in your KV cache in order to saturate your in order to leave this bandwidth bound regime, and so you're kind of leaving performance on the table. You could be putting more tokens through your model for free, but you can't because the KV cache is saturating it. And another thing starts to happen as well, which is that the memory bandwidth, the time it takes to move this entire KV cache into your SMs, also becomes an increasingly large component of the inference time. Usually you can disregard this. It's much smaller than the time it takes to perform the feed forward layers of the model. But at high batch inference, for example, we can put some numbers to it, at something like 32K input and 1K output, running with a batch size of 8 on a 1/H100, this Quen 30 billion, approximately 45% of the inference time is spent pulling the KV cache from the high bandwidth memory into the SMs. So this is a very significant chunk of inference time. But like in the low inference case, in the low latency inference case, speculative decoding can help amortize a lot of these costs. So let's take this example where we're very strongly bound by the KV cache occupancy. Each request has 100,000 tokens, so we can only fit 10 requests in our KV cache. If now we can if now we put in 5 tokens per request that we speculate off of, we bump this up to 50 tokens per request, and maybe at the end we get, rather than 10 tokens per, I'll call it like a clock cycle, per like forward pass, per like decode pass, we'll put 10 tokens per decode pass. Maybe if my draft tokens are really good, this will result in 30 tokens per decode step. And the nice thing is that because I'm still very firmly in the bandwidth bound regime, 50 tokens is obviously far below the sort of 5,000 token limit to which you're bandwidth bound for the Quen 30 on the H100. And this isn't increasing the amount of memory I need to pull in from my KV cache, so I'm amortizing this time here. And I'm able to get 3 times higher throughput in this scenario than I would be if I wasn't speculatively decoding. And for a dense model, this tends to not be the case, just because if you're in this sort of regime, the small but many request regime, the dense model, is going to be so strongly compute bound that speculative decoding wouldn't help you here, and you would want to turn it off. But for MOE models, you can still use it even in this regime, and it can help as well as helping in this sort of long context regime. So we talked about why speculative decoding might be useful here, but let's talk about like an adaptation to speculative decoding that would be specifically designed for this high batched API regime. So typically with speculative decoding, you have your draft model runs online and blocks the big model. So when the big model wants to do a decode step, you first run your small model. Maybe you run it 10 times to get your 10 tokens that you're going to speculatively decode off. And during this time, the big model is blocked. So the big model does nothing. So the blue model is the draft model, the orange model is the big model, and run. It doesn't run at all. And then during the big model's decoding, the small model has to wait. It doesn't do anything, while the big model does its singular pass to speculatively decode off of those. And if the small model is small enough, this is fine, and it's very useful for low latency inference, but it is a bit wasteful of resources. Remember, your big model sits on its own, your small model sits on its own set of GPUs, and your big model here sits on its own set of GPUs. And so while this one's working, this one's idle, and while this one's idle, this one's working. And so to some extent, you're wasting your GPU resources, which isn't nice. In the batched inference regime, the situation looks a bit different because not every request comes back straight away. You have a queue, and your queue has various requests in it. And then you have your model, which is dealing with, let's say, 64 requests at the same time. And so this is going back and forth. This is like endlessly decoding, and you have a queue of many thousands, tens of thousands, hundreds of thousands of requests waiting. And in a typical batched API, you offer sort of something like a 24-hour or a 1-hour SLA or whatever. So requests might be sitting here for quite a long time before they're processed by the model. What you can imagine doing in this time is taking your small model, pulling requests off of the queue, generating your responses. So now you have your tokens that you have that you've generated, and then writing these back into the queue, and you update your sort of data structure in the queue, such that now the request that gets pulled into the model when it's finally used is the original tokens plus the draft tokens that you think make sense, are good sort of speculative tokens for this model to potentially use. And so offline, while these requests are waiting in the queue, you can slowly speculate off them at the same time that the model is working on previous requests. And then your model has a constant source of speculative tokens and then never blocks and waits for the small model to run. And this is obviously a more efficient use of GPUs. You're kind of pipelining both the draft model and the big model, hoping to get like a global throughput that's higher than waiting for the small model to run, especially when your high throughput inference is mostly bottlenecked by KV cache occupancy, and you don't want, let's say, one of your GPUs in your node to be occupied with a small model doing draft tokens when that could be used for KV cache tokens. So it's nice that the model in this case is completely separate to the big model. It could run on CPU, even depending on how small the model is. It might be just a database of past model responses that you use to populate these requests, to draft these tokens. It's nice that it's completely asynchronous to the big model. Unlike the traditional use of speculative decoding, what you're appending here are tokens rather than logits. In typical speculative decoding, in order to make the speculative decoding truly lossless, you need to have the logits with the model with the model themselves, and that tends to be how it's done. But there are a few tricks to make this work. The LLM, for example, supports n-gram speculative decoding, and this would be the kind of thing you use along with that engine in order to achieve speculative decoding. So to recap, today we talked about speculative decoding a bit. We talked about what tends to limit high batch, high throughput inference, which tends to be your KV cache occupancy. We talked about how with modern open source MOE models, the ratio at which the number of tokens at which you become compute bound is much higher than it used to be for dense models, which makes speculative decoding useful in a much wider range of situations. And finally, we talked about a slight adaptation to speculative decoding, which makes it more suitable for batched API inference, which offers long-term SLAs like 24 hours or 1 hour. Thanks for watching this video, and we hope to see you again at the next one.